So please, the next speaker, come to the stage, Weijia Sun, who's presenting on how to mitigate the effects during the observation time for the foremost sensor.
Hi everyone, my name is Weijia Sun from Leibniz Institute for Astrophysics Potsdam, IIP. Really glad to be here. So Olivier has just given an enlightening talk on the ever-present issue of the satellite contamination with our spectral survey. Now, I'm going to dive deeper into one specific case, foremost, and present our solution here. So my colleague, Genevieve, has talked about this briefly in the morning, and I will present much more detail on that. To begin with, what is foremost? So foremost will be a wide-field, high-multiplex fiber-fed optical spectroscopic survey facility for the ESO's 4-meter telescope, and will be operated in the Parnell Observatory. It will be the only equipment installed on the Vista and fully dedicated for the ESO's public survey for the next 5 or 10 years. So it will be featured with a large field of view, 2.5-degree diameter in the field of view, with over 2,400 fibers located in the focal plane. This is to say that we have the capability to observe more than 2,000 objects simultaneously. And at the end of the first 5-year survey, we'll be observing over 25 million targets. It has 3 spectrosgraphs. 1/3 will be fed into a high-resolution spectrograph resolution around 20,000, and the other 2/3 will be fed into a spectrograph of a medium or low resolution, whatever you name it, of resolution around 6,000. So right now, the foremost is under the final assembly and test phase in Europe before the shipment to Chile, and we expect to see the first light in Q2 next year, and the operation will hopefully start in Q4 next year with at least 2 of the 5-year survey. Of course, foremost will have a huge impact on a lot of science themes. For example, we know that the chemical abundance and the kinetics of stars is correlated with its birth environment, and foremost will complement Gaia by providing the chemical abundance and radial velocity for the faint stars. And for cosmology, the foremost will measure the radial redshift for the galaxy and the quasars to complement the Euclid and measure the cosmic expansion history and the growth of the matter. But these are not the topic of today. So let's first look at this beautiful sky the foremost will see. So this is a Vista telescope on the Parnell Observatory. And you can see the beautiful Milky Way. The Magellanic Cloud is probably somewhere here. And there are some green and red air glow. I don't think you can see it from the presenter, but there is just a fantastic view. But in the near future, it could be something like this. So this is a simulated all-sky plot of the satellite trails of 50,000 illuminated satellites seen from Rubin Observatory in Chile in a 10-minute window time period around the twilight. So it's estimated that in the next decades, up to 100,000 or even more, based on a lot of talk today, will be launched into the low Earth orbit very soon. And at Parnell, where the foremost will have, there will be over 5,000 satellites over the horizon at any given time. And for foremost to be more specific, we expect to have in each 20-minute exposure, there are around 60 trails entering the field of view of foremost. And although the foremost has a rather sparse fiber configuration, so each single solid circle represents 1 fiber, different column represent different spectrograph it will be fed in. You can see there's quite a gap between them. For each trail, it will, on average, hit 1.3 fibers. So this will give us 80 trails affected, or let's say 3% of the total fiber, which is definitely not a small number. Of course, this kind of estimation depends on the elevation of the sun. So let's say several hours after the twilight, this number will be much smaller, but on average, we are still likely to see 20 fibers affected. The next question is, okay, so which kind of targets is more likely to affect it? So basically, the targets of the foremost can be classified into two groups, either stars in the Milky Way or the distant faint galaxies. And it turns out that these faint galaxies are so faint that they cannot be observed by a single visit. That is to say that we have to go back to the target multiple times to achieve the signal-to-noise ratio required by the surveys. And so multiple visits basically counteract any satellite contamination one visit may have suffered. So galaxies are mostly likely fine. And we focus more on the result of the galactic pipeline. So for the interference of the satellite contamination on the stellar labels as a function of, let's say, effective satellite magnitude, we simulate the foremost spectrum for an entire whole night. And for another night, we have the same targets, but each of them are contaminated by a random selected satellite. And we look into these two nights are reduced by the L1 pipeline and then further analyzed by the L2 galactic pipeline. And we look into four abundance, so four parameters, namely the radial velocity, the temperature, the surface gravity, and the iron abundance. So you can see we have a significant increase in uncertainty for the radial velocity and the iron abundance as a function of satellite magnitude. While for the other two labels, the effect is much more minor, but we still see the uncertainty in the temperature is noticeably larger, and we even have the slope of the surface gravity becomes negative. So this means a bias is introduced in this analysis. So therefore, we have shown that the influence of the satellite exists, but in a subtle and substantial way, which cannot be easily detected by our galactic pipeline or the quality control pipeline. And the best, or maybe the possible only way, is to use a dedicated imager. So here comes the satellite imager for the foremost. So we will have a small camera mounted in parallel to the foremost to monitor the field of view and detect any incoming satellites crossing the field of the foremost during the operation. So basically, we have three requirements or features. So it needs to be real time, which means the system delay from the moment we receive the exposure to the moment we know there is a satellite should be within seconds. Secondly, the system needs to be always on. That is to say that the scanning blind time should be close to zero. And we hope it will have no reliance on the external information. So this is to control the entire level of the complication. So here are some key design specifications we have for the foremost satellite imager, and I'll explain why they have. So first of all, for the field of view, we expect to have a larger field of view to cover the entire field of view of the foremost at any orientation. And so this is a map of the focal plane of the foremost field of view in the focal plane in millimeter, I think. And after considering the patrol radius of each fiber and a safe margin to have reliable satellite trail detection, we set, let's say, a field of view of 3.5 degree times 5 degree. So this will give us an entire field of view of 17.5 square degree, which is roughly 4 times of the initial field of view of the foremost. As for the exposure speed, we note that the effective exposure of the satellite does not depend on the imager's exposure time, because the satellite is moving different from the star. However, there are still two limits we can consider when setting this exposure speed. So on one end, we consider is actually the rotation of the imager. Since we will not have a rotator for the imager, and during the operation, the field of view of our imager will actually rotate around its center. So the stars far away from the center field will leave an elongated trail, which should be avoided. So this gives us an upper limit of roughly 2 seconds. And at the low end, we consider let's say, the shortest traversing satellite without crossing the field of view foremost. So this is indicated by this green short line, indicates this minimum traversing time, which is roughly 0.5 seconds. So between 0.5 and 2, we choose 1 second, just for convenience. And the next parameter is about the pixel size. So in the end, we want to achieve a precision for the spatial resolution to be 1 arcsecond. This will allow us to figure out which exactive fiber is actually hit by a satellite trail. So after pixelizing our mock image with different pixel scale, we can find, okay, roughly 3 arcseconds per pixel is good enough for this purpose. And in the end, we also consider the aperture. So this is this is to make sure that we will have enough signal-to-noise ratio for both the stars and the status trail we want to do the identification. And in the end, we choose an aperture of 13 centimeters, which is a very small telescope. But here are all hardwares. And this is just to allow us, we have the capability to see what we need to see. But we still need the hardware to make it work. And in this job, there are basically 2 tasks. One is to solve the astrometry, to know where the telescope is pointing and where we are. And the other one is to detect the satellite trail. So whether or not there is a satellite in our field of view and where it is, and what can we learn from it. So we built, for the first one, we have an astrometry module, which is based on the astrometry.net software. And for the second task, we have 2 modules. One is trail fast, and by the definition, it can tell you whether there is a trail in a fast way, but rough information. And the second one, we call it trail slow. It's much more reliable, but takes much more time to calculate. And based on our estimation, only less than 5% of the image we will take will have a satellite on it. And from our perspective, the rest 95% is just useless. So we designed this workflow like this. So it will go through a trail fast module first. And if there's no trail found on this image, they are just discarded. And for the rest 5%, they will go through the astrometry module, then feed into the trail slow to learn all the information we need. For example, the location, the width, and the brightness of the trail. And in the end, this software will cross-match with the observation block for the foremost and to mark which fibers are actually contaminated by the satellite. Okay, so these are some simulation. I will just skip them for the sake of time. So this is how we do the trail slow. We use, actually, I think in the morning's talk, the software developed by the ACS tools. We use that and to have a very reliable determination of the satellite's location. So in the end, based on all this kind of simulation, we can find a very good performance on the astrometry, around 1 arcsecond, considering the spatial resolution, the pixel size is 3 arcsecond, this is quite good. And for the trail detection, we have, let's say, for the most of the for all the tasks, actually, with no trail in the field, no trail are reported. So this is to ensure that we don't have any false alignment. And for those who have the trails, we can have a success rate of roughly 100%. And based on this optimization of the data flow, we can achieve much shorter runtime of this whole system, roughly within a few seconds, to keep pace with the input speed of the data. So what's next? So in this year, a test platform will be mounted on the building of the AIP to test all these kind of specification and whether test the data flow, whether they can really do what we hope they will do, and we can also test whether we need to do some differential photometry based on these data. And once these fibers affected by the satellites are flagged in, let's say, in a real operation, and most importantly, we know the information of the satellites that will polluted them, we can better recover the stellar parameters which may have been introduced a bias by the satellite and maybe introduce some machine learning model, see the talk later. And by this approach, we will build, let's say, an archive for the satellite contamination, which can or may not help improve our understanding of the satellite and design a better observation strategy to mitigate the effect of satellites on our astronomical observations. That's all. Thank you.
We have time for one question.
Yeah, really great job. This is Siegfried Eckel, IAUS and CPS. First of all, a remark, please send us that data, even the test data, we'd be really happy to have it. And the second thing is, I've heard a bunch of times now that with machine learning, like you can mitigate some of the effects that satellites harm. But don't you think that you can also introduce some other artifacts due to machine learning not being perfect that you then have even a harder time to getting rid of? Because I'm afraid that if we just say machine learning can solve everything, we're just giving people a blank check to do whatever they want.
Okay, so well, the machine learning stuff has basically haven't been developed for this purpose. I think latest talk will answer your question better. But in my point of view, with a dedicated imager, we can, let's say, in most cases, we don't need a machine learning to do the job. Right? We know which fibers are actually affected. And for those even affected, we can know the degree of the, contamination much better if we don't have, compared to the case we don't have information of the satellite. That's why I think, well, a dedicated imager is still necessary. And yes, of course, the machine learning can introduce some bias or some ghost in the data analysis. And that's the reason why in the first step, when preparing all this kind of stuff, we still need either the imager or an ephemeris to make sure that our conclusion is right or reliable. Yeah.
Thanks again, Weijia.